Laminated glass is several layers of glass connected together by a foil or bonded together. This is some kind of trivia, but we have to start from the basics. The purpose of laminated glass. Well, laminated glass have a variety of purposes. First is safety against falling out. So big IG units in skyscrapers, balconies, balustrades, all kinds of security corridors is all lamination glass focus. Of course, sound insulation, we will be going in detail in the second part of the webinar. Burglar resistance against those who want to break in or maybe break out for that case. Hurricane resistance. Now, this is especially important for America. It has a lot of standards about it. For Russia, we don't have any standard about hurricanes. We just assume it is a very high wind. But hurricane resistance is has a lot of nuances in it. Of course, it is resistance against blasts, explosions. Laminated glass offers great protection against ultraviolet. So if you are having a picture gallery or something similar or exhibition, then you have to protect it with laminated glass. Because used ultraviolet is great at damaging the paints. And of course, the structural elements like columns, pillars, lamels, and so on. These are usually made from very thick glass, very thick lamination glass. Maximum lamination thickness which I have encountered is 100 millimeter. And that is a quite difficult thing to make. Let's go. At first, we need to see what makes the glass resistant against, for example, an impact and how the foil behaves. For that purpose, we'll be watching several short videos on course of the webinar. And this one is great because it not only shows you how the glass reacts to ball drop test, but it shows it in slow motion. So let's watch the video. Oh, sorry, let's watch it again. You see how the glass will be bending upon impact. Now, that is what makes this video a very interesting one, the slow motion part. Before we watch it again, see for yourself two things. First one, see the area around immediate impact. This is a laminated glass made from normal glass, not tempered, not heat strengthened. The central area, which got the most of the impact force, received a lot of damage. So glass here in the epicenter doesn't have any structural properties anymore. It is only the film, the foil, which holds the glass together and stops the ball. Also, when the ball falls, see how the lamination glass behaves, how it moves with the impact. Let's watch it again, rather short one. Now watch the move of the glass. Why is it moving? By changing its form, glass and the interlayer, the film interlayer is absorbing the energy of the ball impact. And that is very important because when the impact, when the ball hits, yes, glass have something to say when resisting the damage. But it is the foil who takes the most and this is the foil who is dampening the energy of the impact. The foil has one important property, and the property called shear coefficient. And these we will be mentioning several times in the future, but now remember how the glass reacted to the impact. And with that knowledge, let us proceed. First, we want to talk about the structure of the polymer from which the foil is made. There are different types of foil and different types of polymers, varied by their structural properties. So at first type of foil which we'll be talking about is thermoplastics. The example is polyvinyl butyral, or PVB, very commonly used. Thermoplastics have a relatively weak intermolecular forces and usually have a linear, like this. So this is a structure of polymer molecule, or slightly branched, like a tree, structure. They are thermoplastic. So that means that if they, for example, heated from one temperature to another, their properties will change, but when cooled down, they will be having the same properties as before. So yes, they are reacting to the temperature, but when the temperature changes back again, nothing happens. Second one, we'll be looking at elastomers. Now, from the name, you can see that they are elastic. An example of elastomer is EVA, or ethylene vinyl acetate. And they have another system, which is, you can see here, it's cross-linked. This type of film also changes its properties with the temperature, although in the slightly different way. And another example of this system is a silicone. So, for example, you can easily stretch the silicone, and when you release it, it goes back. So they are very elastic, soft, and they are return to their form if the force which was stretching them releases. The third type of polymer is thermosets. They have intertwined, means very much intertwined structure. The example here, we will be briefly mentioning them during this webinar because they are not really the scope. And these are not the foils, but these are the polymers which are used mostly for making of anti-bullet or bulletproof glazing. The examples of epoxy resin is good enough. When you make it, when it stabilizes, it cannot be reshaped any further. It can only be broken. So with this 3D polymer structure, when it sets in forever. That property helps a lot when you're making bullet-resistant glazing, because with those types of polymers, they are very good at stopping the bullet impact. But bullet resistance is a very specialized topic. We'll be avoiding it for today. Let's take a look at each of the most common films individually. And we start with the PVB, polyvinyl butyral. One of the most common foils. It has every type of foil has something good and something which is not. So it has its advantages and disadvantages. And PVB is no difference. The good thing is that it blocks ultraviolet almost completely, starting from the 0.76 millimeter thickness. And talking about the thickness of the films in laminated glass not measured in millimeters. It is measured in the films, so to say, or foils. So one foil is 0.38 millimeter. So, for example, if you see a lamination glass like 663, That does mean it has 2 times 6 millimeter glass and 3 times 0.38 millimeter foil. That means 1.14 millimeter. That's quite easy, but not mistake them for millimeters. PVB films have a different type of production, but most commonly they are produced in an autoclave. And a little bit of a disadvantage for a processor is that they require special storage conditions on the production facility, because they have to be stored in a cool and, most importantly, dry place with very low air humidity. And this is a disadvantage of PVB film, because most of the standard types of PVB absorb water from the air quite easily. If it is absorption happening on the ready-made product, the delamination process, meaning breaking apart of the laminated glass, will start. That is called a hydrophilic material, meaning it attracts, likes water. If you want to use PVB in, for example, balustrades or balconies in the wet conditions, then you have to ask a PVB film supplier for a special PVB type. They usually have one, which are more resistant to the water. For example, some of the PVB films can even be used in the shower cabins, which are quite humid environment. And another one of the PVB properties, and that is viscoelastic. Remember, like a thermoplastic, change the parameters with the temperature. And that actually can be quite a problem if you are using PVB film as an PVB laminated glass as an outside glass in a very hot and sunny environment. Because starting from 40 degrees, the shear coefficient, I mean, remember, the one which is responsible for the behavior of the film, starts to drop down. And PVB starts losing its anti-burglar, anti-impact capacity. It completely loses its capacity at a temperature around 75 to 80 degrees, meaning altogether. So glass with a PVB should be avoided in using in such environment. But in the temperature range from minus something to plus 35, PVB performs excellent, especially under short loads. So ball drop, wind impact, PVB performs excellent at all of those conditions. Next up on the list, we have Ionoplast interlayer. Now, here, unfortunately, I cannot avoid naming the brand because it's extremely common. It is Sentry Glass Plus, made by Curaray or Trocifol. Those are branch and brand companies. But, and it has very high tear strength and rigidity, very rigid film, up to a point that the film itself has a holding capacity. We will see the videos, but now watch the picture on the right, the photo. These are two temperate laminated glass where the glasses are being broken in both cases. On the right, there is a conventional PVB. On the left, there's Ionoplast. You know, you see, you see, it is still holding almost horizontally. So the interlayer has its own capacity to carry the load. It is only the interlayer that is holding it in the horizontal position, not letting it drop like a normal PVB. And these properties are because Ionoplast is a very interesting type of polymer. In its polymer structure, it has crystalline clusters, which are distributed all around, and they have such a structure that they give a very high shear coefficient and very high rigidity. Ionoplast is full of excellent properties, meaning it is very rigid. It is very resistant to blasts, impacts, loads, offering a very good security. Always retains its clarity. It means it will not go yellow over time. Very low haze index, very transparent. Water, moisture doesn't do anything to this material. Those are advantages. Disadvantages are very high price compared to the other interlayers, and by very I meaning really much higher. And the thing is that it is really difficult to process on the glass processing factory, which adds even more to the cost of the lamination made with the centric glass. A lot of problems that can be here, that like it has a best adhesion only to the thin side of the glass. It accumulates static charge, and you know the static charge, if you have a synthetic pullover, it attracts all kind of dust. So it has to be cleaned regularly and thoroughly. Very difficult to cut, so it requires special regimes when produced, so very tough to produce, but if you make it, offers a great result. One of the disadvantages is also that it cannot be used with any other type of interlayer. I mean, no PVB, no EVA, and it doesn't have any coloration. I forgot to mention that PVB can offer you extremely wide variety of color variations. Blue, green, bronze, gray, red even. It goes in huge variety of colors, and what is better, those colors can be mixed together. For example, you have one blue and one gray PVB film. You put them together in a lamination, you make a blue-gray. So color variation are really limitless in the PVB by mixing all of these colors together. And that is good because PVB you can mix milky, opaque film with the normal film, transparent, and make very thick, very tough lamination. So really a lot of variety here. Centric glass offers no such thing, but it is good in another fields. Where is it used? Mostly it is used in the very hot regions because the temperature limit at which it loses its capacity is much higher, around 90 degrees. It is used in the very humid areas, but mostly it is used for glass floors, glass steps, overhead glazing where you expect high load on it. So glass floors are the most common one. And in some regions it's used widely, namely because it has a very high temperature limit. The third interlayer which we'll be looking today is ethylene vinyl acetate, EVA. This is a copolymer of ethylene and vinyl acetate. And this is elastomer, remember? Very elastic one. So comparing to PVB, EVA is softer, more elastic. And from this, there are pluses. Plus is that it offers good sound reduction values. It has very high adhesion to almost any materials. So if you want to put something make something of an artistic, like an artistic triplex, like an art, to put some leaves, anything, branches inside the lamination. So EVA has a great adhesion to all of these materials, almost all of them, to metals. If you want to glue a glass and metal together, EVA is the way to go. It's even used as a glue in support structures. Outstanding heat, humidity, ultraviolet ray durability, perfect reliability in the long term. The properties doesn't degrade over time. So EVA is great overall, but it has its disadvantages also. Because it is softer, it has lower impact resistance than the PVB. So for example, against ball drop, axe, bullet, all of the sharp concentrated loads, EVA shows worse than PVB performance than PVB. Those are the disadvantages. So if your building doesn't require any strict safety or security standards, EVA is a perfect way to go. If they do, you have to go for a PVB or even for SGP in this regard. Also, it has yellowness index, usually, not always, worse than PVB. Some modern EVA types have very low yellowness index, meaning they are very transparent. And yes, ultraviolet is better blocked by EVA than PVB. Moving forth, let's take a look at the process, how they are made. For a PVB or Ionoplast SGP, you require 2 stages. Stage 1 is pre-lamination. You have to have this line. At first, glasses comes through the washing machine. In proceeding, when you laminate and make a sandwich, glass, film, glass. After that, it's moving to the colander or pre-lamination chamber. Here it is heated up and rolled between two huge rollers made of resin, which are pressing it and pushing out all air, excessive air, because you don't need any bubbles in the end. After you pre-laminate your sandwich, you're putting it into the autoclave. There, you apply pressure of around 12 atmospheres, high temperature, depends on how do you do, but usually around 180 degrees. And there, a polymerization of a material really starts. So it catches up with the glass with adhesion. It becomes transparent. And if you have any microscopic bubbles of air or even visible bubbles of air, they are dissolved inside the film. So it's cleared up, and in the end, you get your product. That is for PVB and SGP. If you're talking about the EVA, process is much easier. You're making your sandwich in the clean room, as usual, but you don't require any pre-lamination. You just put them on these stories inside the silicone bag. Then you connect pipes, suck out of all of the air there, so creating kind of vacuum, and then put it for a short time in the heating chamber. In this heating chamber, EVA sticks to the glass, and in the end, you get the product. EVA is also good that you can make a lamination of the EVA using an autoclave. You can even laminate it in the heat soak test chamber if you don't have any other equipment or if your equipment is overloaded. EVA is it's really not asking much in this regard. And after we watch the process, let's see how the glass and how the shear coefficient is affecting, how the rigidness of the foil affecting the behavior of the glass. This is a laminated glass, 2 times 10 millimeter, tempered. And the guy will be breaking the glass one by one. This is a movie again, so watch it. But notice, remember the previous webinar, how much time he needs to strike in the corner of the tempered glass, the most vulnerable part of the tempered glass, with the sharp edge of the hammer to get any results. Let us see the video. Four or five times, I guess. So tempered glass, thick tempered glass is quite a resistant thing. But you see how it goes. It immediately loses all of the carrying capacity and slowly but surely goes down. Now let's watch the next video where you have a special film, which is very rigid. And to add more, you have 70 kilos of sand in the bags on top of it. Let's watch how it will behave. It will not go down. It will stay as it is. So that is how centric glass is behaving when you break the glass and leave only it, even under the load. The question is how to make almost the same effect, but cheaper. We have actually talked about this on the last webinar. You make laminated glass, not with a tempered glass, but with heat strengthened glass. And there, glass will hold, not only because film is holding it, but because it breaks into bigger pieces and the pieces of the glass will be holding it together. Unfortunately, I don't have a video of a heat strengthened glass, how it will behave in the same situation, but it will behave much the same way. So, kind of alternative. There are some standards, European standards, EN, which are used for different types of tests. And just the general standard of laminated safety glass, the one we are usually referring to. They're usually not free to download. In Russia, we are quite lucky because most of our standards are in line with almost the copies of European ones, only that they are translated into Russian and they are free to distribute. So if you know Russian, you can read almost all of them without paying anything. But that's it for the introduction to laminated glass today. And I suggest that we move on to the acoustic properties. If you got any questions, feel free to ask again. To begin our talk about the acoustics, we need to talk a little bit what is sound and how do we hear it. From the point of view of physics, sound is a mechanical wave which has a different properties when passes through different types of media, meaning air, water, steel, for example. But in our perception, is that how our brains interprets the incoming sound waves which are received through our ears. So we have a receiving apparatus that are our earlobes, and we have a brain which interprets the signal. At first, let's talk that human ear perceives sound waves in a lot of frequencies, started from 20 Hz and up to 20 kilohertz. The interesting thing is that as we age, our ears perception degrading. So the more we are moving for being grandparents, the less we hear in the high frequencies. But that's nature, everything deteriorates in time, so let's consider it normal. But the thing is that sound waves are much more than the human ear can catch. If we get sounds below 20 Hz, it is infrasound. For example, whales communicate with each other with infrasound on infrasound frequencies easily. And for example, bats, they are ultrasonic. They communicate on ultrasonic frequencies because it's easier for them and it's needed for them because they have a radar of their own. But you see, sound can go in a lot of frequencies, started from low to high. And usually what we need to do, we can describe the sound wave. So telling on this frequency, you have this power. On this frequency, you have bigger, and so on and so on. So we can look at the frequencies range and set the powers for each one of them. That is scientific, but it's not very good for interpretation. And it's not very easy. For ease of us, the decibel scale has been developed. And decibel scale, main purpose of it is to say that to interpret the power of sound in one number, which will be adapted to how our ears perceive it. For that purpose, decibel scale uses this formula, but we will not go deep into mathematics, and we will look at the graphs. Yeah, the most important thing here is that the formula itself is logarithmic, and logarithm has a base of 10. Very important. And what it means, I will tell you right now. Sound level, noise level is measured in decibels. But because the scale is logarithmic with the base of 10, that means every 10 decibels, the perception of sound for human ear is doubling. That means that 90 decibels is twice as loud as 80 decibel for us. So every 10 decibel, the volume doubles for our ears. That's the consequences of a logarithmic scale we're using for decibel. What about sound reduction? Sound reduction is the property of some kind of material or wall, for example, for our window. And that does mean if outside we have 80 decibel noise, and inside we hear 50 decibel noise, then the sound reduction of our window is 30. So 80 minus 50. If, for example, we want to make our window or a facade to block twice as much sound, then we need to make it 40 decibel sound reduction. That means inside we'll be hearing 40 decibels only. 10 decibels less, twice less sound for us, half. And that is very good, but there are some more nuances into it. At first, logarithmic scale, I mean, the proper logarithmic scale looks like this. Sorry. Quite difficult to paint with my mouse, so it's not a proper logarithmic scale, but you see. And the beginning, if you have small difference, it's not much. But the more difference we have, the bigger difference for our ears. So this is a decibel. And this is our ear perception. So if we talk about numbers, the difference between two sources of sound, if it is 1 decibel, for example, we have two speakers. One is here and one is here. We are listening to them. If the difference in the sound level is 1 decibel, and we can barely hear it. So yeah, maybe this one is louder, maybe, but I'm not sure. 3 decibel difference is almost, but surely perceptible. We say, yes, this one is different. If we got the difference between these 5 decibel, this is a clear difference, meaning, yeah, this one louder and by a small margin. Right? 10 decibel, twice, doubling or halving. And that is very important when we will be looking at acoustical properties of an IG units. Remember these numbers, and then we move on. Several more letters to understand. So again, remember, if we want to properly describe our sound, we need to make a scale with all of the frequencies and sound levels. And this, the summary of it calls sound reduction coefficient, or R, without any indexes. RW is our main number with the sound insulation, sound reduction, because it is derived from SRI, sound reduction index, directly, but it is applied to the scale which takes into account the sensitivity of our ears. So this is how we humans perceive the sound. So this is our main number. But along with it, we have a sound which can come in a different frequencies. And there we have two correction coefficients. First one is the correction coefficient C. And this one is used for a medium to high frequency sound emitted by road traffic on the high speed, railway traffic on the medium and high speed again, jet aircraft, so on. So this correction coefficient is subtracted from R to make effect. So if your sounds are coming from a specific source, then you should use this coefficient. Another coefficient is a traffic coefficient, which is used most frequently because it is dealing with the low frequency noise. And low frequency noise has a greater penetration of all sound waves. Imagine if your neighbor is listening to the heavy music and listening loud. You have closed all of the windows in your house. What will you hear? You will hear something like boom, 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 boom. Very low frequency noise is still coming. You won't hear anything apart from this, from the beat, but you will hear the beat because it goes on a low frequency. So you need another correction coefficient to see how your IG unit will behave in a low frequency situation. Usually it's spelled like this. So you have tested or calculated sound properties of your IG unit and you get the result. So RW is equal to 42. And then you get -2 -6, something like that. So this is RW, this one. The first number is C, the first coefficient from medium and high frequency noise. And the second number is C traffic. So the sound reduction for this noise will be 40. And for this one, it will be 36 decibel. Because these numbers are directly subtracted from the main parameter. Now, it is very important if you get a request from the client for some kind of noise reduction IG units, it's very important to understand what exactly is the parameters that he's asking for. Because if he's asking about low frequency noise reduction, then you need to use this one. Let us move on. Again, if something is not understood, if you got any questions, feel free to ask. Now that we deal with the parameters, let's see how the glass sound reduction goes different depending on the frequency. Here we got a graph of sound reduction for monolithic 10mm glass. And starting from the low frequencies, you see it's steadily, almost steadily goes up, 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 up. And at some point, the sound reduction values are dropping. And then they are back on the track again, rising. So why is this drop happen? Physics knows the answer in this case. Because what is the monolithic glass from the point of view of physics? It is a single sheet of glass having a certain mass on which you are putting your high energetic sound wave. Because it's a glass sheet, and the sheet with a certain mass and a certain properties, it has its own frequency on which it can resonate. So if the frequency, if the self-imposed frequency of this sheet is equal to the frequency of the sound, then it will resonate with this frequency. It will not block the sound on this frequency. It will increase it in this frequency range. So this drop is called a coincidence dip, because coincidentally frequencies are the same. And this coincidence dip is depending on the mass of the glass. So the heavier the glass, the more this coincidence dip moves in the lower frequencies. Let's take a look at something interesting. So how do you really improve the acoustic properties of your IG units after all? One of the most important, go for thicker glass. Thicker glass, meaning they are more massive, they're having more mass. So they will be better at blocking incoming sound. And the thicker the glass, the better it is at blocking low frequency sound, because it's heavier. Okay, one glass is good, two glass is even better. So IG unit with the two glass and gap between them is better than a monolithic one, usually. But for the IG unit, there's a third rule. Use different thickness of the glass. That is because they have a different resonance frequencies. And if you make an IG unit with two types of glass with the same thickness, they will resonate on the same frequency. And your drop here will be even deeper because they are connected into the system and will resonate together. increasing each other's vibrations. So thicker glass, different thickness of glass. Then there is a doubtful one, like increase your spacer width. I wouldn't recommend for this one, because to have any real effect, you have increased your spacer thickness by 20 millimeter, which is almost always impossible. So in my opinion, I would have dropped this one. Then the third one is to use laminated glass. Why is it good? Because it has interlayer which dampens the vibrations upon receiving the sound wave. Even better when you have a special acoustic interlayer. And we will see in the next slide, we will see how it behaves. The one thing is that argon filling or krypton filling does not improve your sound reduction in any way, shape, or form. Those gases are not for it. They are for U value and U value only. So out of this list, I would make 3 major ones. So this is thicker glass, different thickness of glass, and lamination and acoustic lamination. I'll count this as 1. So how does the lamination glass behaves when we look at the graphs? Very interestingly. You still have, see, I need to have changed the color, sorry. And this one, the blue one in the bottom, this is our 10 millimeter glass, which we have been looking before. The yellow one is the laminated glass 2 times 5 millimeter with the normal film, standard PVB. What you see in here you see this pit again, so the graph will fold again. Now, why is that? That is because PVB in these frequencies, it is so harsh, it holds the glass very hard, and it is very hard itself in this case. So sound, from the point of view of sound, it sees this lamination as a single 10 millimeter glass, just a slightly better. But if we install acoustic PVB, which is softer and far better at blocking these vibrations, so it's asked as a viscose interlayer between those two, you will not have this gap. So that is how the acoustic PVB, why is it is better than normal one? Because it is softer and it is blocking the sound especially in this case, much more efficiently. That's why we need to have an acoustic PVB or EVA for that matter, because EVA is also soft and a good noise blocker. Let's take a look at the numbers. So if we got RW on a very standard IGunit, it will be around 29 decibel. Different types of glass, different thickness of glass, a little bit more. Remember, 1 decibel difference is nothing. 10 decibel difference is doubling. Single sheet of 8 millimeter, heavier, more solid, again an increase. Thicker the glass, even more. Laminated glass, even more. And then we have an IGunit with the laminated glass and acoustic laminated glass. And now overview this table and see how far we had to go from our 29 decibel to 40 decibel. So in order to make this IGunit to be blocking twice as much sound, we had to go from a very basic formula to a quite a sophisticated one, meaning with laminated glass, thicker glass. So this one is much heavier and much costlier, but it blocks the sound twice better. What is the maximum, you may ask? This is a test report for a triple IGunit, triple, with 2 times laminated glass, so 6 and 6 millimeter and 4 and 4. Already much more sophisticated IGunit, and it has RW of 50. Yeah, also see these coefficients, right? 50 decibel. If you increase the thickness of individual glass in the lamination, you can go up to where I would say maximum is 54. But that's about it. And it requires a very heavy, very big, and very expensive IGunit to make. In order to consider using this, you need to understand one thing, that if you want to have a good sound barrier against the sounds, you do not have only IGunit in your window or facade. You are having your profile system, aluminum, PVC, or whatever. And you're having your montage band. So in order to ensure sound insulation, everything on the facade or in the window has to have the same level of sound insulation. If you want your facade to perform at 50 decibel, you need your profile system to have also 50 decibel sound reduction, and that is no easy thing also. Also, to block the sound, you need to be sure that no air is going directly through, because with the air immediately comes the sound. Just come to your closed window here, outside noise, and then open it very slightly. Even with the slightest of air penetration, you get huge increase in your noise level. So be careful with that in the regard of facade design.